And for the last time this semester, welcome back. So, I want to end this class by talking about perturbation theory. And I want to talk about this both because it's one of my favorite topics to talk about. If you've ever met me or engaged me in any sort of conversation, one of the things I'm most interested in is where do analytic approximations or where do analytic solutions actually break down? And once they do, which they always do, and usually pretty quickly, there are only a few tools that we can use to solve them, outside of full numerical simulations, which are also outstanding. Perturbation theory is one of the most powerful things that we can do to try to come up with answers to problems that we don't know based on answers to problems that we do know. And so we're going to be talking about, when we talk about perturbation theory, we're going to be talking about a large class of problems that can be broken down into just that. So in this case, I'm talking about a Hamiltonian, but it really could be anything, right? The Hamiltonian represents the problem in many ways, right? It's where the potential is and it's where the energy comes from, right? And it's always the Hamiltonian is always the thing that I want to find the eigenstates of while I'm solving the problem. So I want to say that my Hamiltonian now is really made up of two different parts. A part, which we're going to call H0 or H naught, which is the problem that we know how to solve. And by that I mean it's a problem that we can use regular old analytic solutions, right? We can solve the problem in position space or as matrices or whatever, but we can solve it for the eigenstates of the Hamiltonian, and I can reproduce what those eigenstates are and what the energies are. But then there's also a little change to it, okay? And we're going to call that H prime. And H prime is going to be some deviation away from the problem that we knew. Okay, we're going to do an example of this on your problem set, but we're basically taking a problem that we know and we're changing it a little bit, and thereby maybe making the problem not analytically tractable. But to do perturbation theory, right, it really needs to be a perturbation, which means, probably from some language, small. And if we say small, as a physicist, you will always say, if somebody says something is small, you're going to say, compared to what? Right? And by h prime being small, we really mean in a dimensionful way that the h prime divided by h, right, that is less than 1, right? That's what it really means to be different. And that is something that we might have to do carefully, right? Because maybe it's maybe the energies of the H prime states are small compared to the energy of the H naught of the H naught states, right? But somehow this ratio of the two dimensional things produce a dimensionless ratio that I can actually compare to 1. And that's going to be important because perturbation theory relies on our intuition of Taylor expansions. And in Taylor expansions, I can only expand in something that's small. I can't expand in something that's big, otherwise it wouldn't converge, right? Or it wouldn't make any sense to truncate that Taylor expansion at any given order. So some people like to talk about this. They like to add a fake tracker, a tracer, okay? And I'm going to do that for this video, but that tracer lambda is going to keep track of how many orders in perturbation theory I have. That is, this lambda that I put next to h prime, eventually we're going to set it equal to 1, right? This is a trick that you may have done if you've taken other courses that use perturbation theory. It's especially useful in Mathematica. But what this is going to do is every time something small shows up, because sometimes it's hard to tell if something's small, but every time something small shows up, I'm going to be able to say, oh, there's 1 lambda, therefore it's more important than a term that has 2 lambdas in it, which is more important than a term that has 3 lambdas in it, right? And like with all Taylor expansions, you can stop once you find a term that's non-zero, right? If the term that has 1 lambda in it is important, then you don't have to do any more, right? So it's a beautiful thing about truncating Taylor expansions that you always want to look for the first non-zero contribution to the changes, and generally that's enough work. So here's the problem: we know, right, that H naught, our unperturbed Hamiltonian, has a set of eigenstates, which I'm going to call psi n 0, right? So that when you have this 0 superscript, that means it's an eigenstate of the unperturbed Hamiltonian, and a set of energies associated with that Hamiltonian, which I'm going to call E sub n naught. Okay? But we don't know what the solutions to the full problem are, right? The h acting on psi n gives us E sub n times psi n. We don't know what those solutions are, although we know they exist. Okay. Now, why do we know they exist? Well, because every Hamiltonian, it's a Hermitian thing. It has eigenstates. There's all the arguments that we have there. But since this is so close to a problem that we have the analytic solution to, right, we can also kind of identify the fact that probably some of our unperturbed states are going to correspond to states of the full system, right? And so trying to link up n for n is not something unusual or something, abnormal to do when you're talking about perturbation theory, because I'm only changing the problem by a little bit. And we'll see that actually gets pretty interesting in just a minute. Okay, so I know the green line. I don't know the red line, but I'm not going to let it bother me because I'm going to now define things that are sort of pushed away from that, that are pushed away from my unperturbed solution. So for every psi n, which is a solution to the full Hamiltonian, I'm going to say, well, that's just some psi n naught, right? Some solution to the unperturbed Hamiltonian, plus lambda, right? That's going to keep track of orders of perturbation theory, times delta psi n. How different are you from the unperturbed solution? Okay. And now I can act the full Hamiltonian on one of these unknown solutions to that equation, right? Psi n. And I can just replace h with h naught plus lambda h1, and I can replace the state with psi n naught plus lambda delta psi n. Right? Okay. All right. Okay. Then, right, I have 4 terms, but what's neat is I can already see that one of those terms goes as lambda squared. I know it's going to be less important than either of the 2 terms that come before it. And on the left-hand side, I have just h acting on psi n. And I don't know what that is yet, but I do know that psi n is an eigenstate of the full Hamiltonian, and therefore that's just going to give me the total perturbed answer to the energy E sub n, right? But this is not an expression for a number, right? If I want to get like what are the new energies of the system, I have to isolate that E sub n somehow, right? Which means that I need to turn this vector equation into a scalar equation. And you can imagine what we're going to do, right? We're going to take the inner product of this thing with another psi n state, okay? And that way on the left-hand side, I'm going to have just psi n, E sub n, psi n, which is just E sub n, right? And I can sort of solve for the new energies. Now that introduces on the right-hand side another copy of psi n naught plus lambda delta psi n. This is the bra version, but it's still another copy of that state. Okay, and so now, if I hadn't done this algebra out, I would have a binomial times a binomial times a binomial, right? Which is 4 times 8 different terms. Okay, but many of those terms are going to be very high order in lambda, right? There aren't going to be a lot of terms left now that are actually going to contribute to this, or at least are not going to be the most important terms that contribute to this. And so if I start to extract, well, what terms don't have any lambdas? There's only one, right? Which is this thing, which of course is just E sub n naught, right? Because, right, that's just the old energy. And so already the new energy is equal to the old energy plus stuff that depends on lambda, right? Because it depends on the perturbation. It turns out if I now look at this, the only term that has one lambda is going to be the term that has psi n naught h prime psi n naught. Okay, and that's really cool. Because I can basically, if that term isn't 0, I can just throw everything else away and not worry about it. Okay? You're saying, Tom, but aren't there other terms? You forgot the ones that look like delta psi n dotted with psi n naught. And I did mention to say them, but I didn't forget that they're 0. And that's because if I'm adding a correction to a state, then that correction is orthogonal to the state I'm adding it to, and therefore those inner products are 0. And that's exactly what we're going to do. Right? We're going to say that the new energies are going to be the old energies plus this little correction. And you might say, is this hard to do? Well, no, right? Because H prime, if it's a matrix, it's a matrix, and your eigenstates are vectors, and it's just one set of matrix multiplication. If you're talking about wave functions, this is just one application of Griffith's rule, right? There's sort of this addition here is something that's a little tricky to think about, but it turns out it's something that's not too difficult to calculate. And what it does is for every state n, it gives us a correction to the energy, which tells us how different is that energy going to be compared to what it was before I added the perturbation. Okay. And I think that that's a pretty cool way of thinking about how to get some answers out, right, in a problem that converges when you don't have to do, or maybe can't even do, the entire problem. And that's as far as we're going to go. I want you in this lecture to both be kind of excited for whatever next quantum mechanics class you take, where you get to spend more time on perturbation theory, because after all, our lives are Taylor expansions, right? But I want you to get the idea that when I have a problem that feels intractable, but is close to a problem that I know how to solve, I'm thinking things like, I know how to solve the hydrogen atom, but if I start to have extra electrons, maybe that changes things a little bit, but maybe not too much, right? And therefore, I can use perturbation theory to learn about how things are going to change just a little bit, or how are things going to change in the presence of an external magnetic field, or how are things going to change when blah 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 blah, right? A whole class of problems that look, when I write down the Hamiltonian, impossible to solve because of their added complexity, are actually pretty straightforward to solve, and perhaps even fun to solve when I have perturbation theory. Okay, take home messages. A perturbation is dimensionless. I have a first order correction to the energies, which I can calculate using this argument that we just had. Beyond that, things get a little bit more complicated, although never as complicated as doing the full problem. All right, well, this has been a semester. I'm actually really glad to have done the class this way this semester, because even though I haven't been able to tell you these things on a chalkboard, I feel like I've really gotten to spend enough time, gotten to spend a lot of time with all of you as we talk about these videos and as we talk about the problem sets. And anyway, it's been a fun time, and I wish you the best.